Hello everyone, today we're going to be talking about section 13.3 dealing with what we call the side-splitting theorem. So the side-splitting theorem is kind of a complicated one. It does have still to do with our similar triangles, but it breaks some of the patterns that we normally try to stick to, which makes it a little bit more difficult. So let me go ahead and write out this theorem. It is a little bit long, but we'll talk through each piece as we go. So first of all, I'm starting with a triangle and I'm going to take a line and put it through that triangle so that it's parallel to one of the sides. So I have if a line is parallel to a side of a triangle and that same line intersects the two other sides at distinct points, distinct meaning different points, comma, then it splits these non-parallel sides into proportional segments. So, couple things with this. Because we're splitting into proportional segments, that means I'm going to be able to set up a proportion. But I have to make sure that I have my theorem satisfied first. So if you look at the picture down below here, obviously this isn't a work. I'm not going to give you one that doesn't work in your notes like this, but we need to make sure we know why. So first of all, I have a line that's going through my triangle. So my triangle is ABC, but I have this line PQ that's going through my triangle. That triangle needs to be parallel to one of our sides, and I do have it marked that it's parallel to BC here. And it's intersecting the other two sides. So in this case, I'm intersecting at P and Q. It intersects AB and AC. That means then that I am going to have proportional segments created by that line. What that means is the top part of one side compared to the bottom part of the other side is going to be proportional to the other top part to the other bottom part. So what I mean by that is the distance from A to P divided by the distance from P to B is going to equal the distance from A to Q divided by the distance from Q to C. So essentially what I'm doing is I'm using the way this is set up. My line going through the middle almost becomes like your fraction bars, and I'm just saying that these two segments divided by the bottom two segments are going to have to be equal. And so if I'm missing one of those sides, we can then solve for it just like we solve with our other proportions. But again, you have to make sure that you have the line that goes through that is parallel to both sides. There is also a converse to this theorem. Remember, converse is just when I take the theorem and I spin it around the other direction. So in this case, I'm going to start with the proportional piece, but I do have to have the same setup. So if a line intersects, and I'm going to use my segments from this picture down here. So I'm going to say OP and OQ at points X and Y. So that O divided by X is equal to X times P is equal to OY divided by YQ. If that happens, and that is actually true, then I know that my segment that cuts through, in this case XY, is going to be parallel to my segment PQ. Okay, so let's walk through that one. Again, it's really just going backwards. So I'm starting with the proportion. If I can set up my proportion with my split sides, and it is important that I have to use the split side from the bottom. I can't use the entire side, so I have to use XP and YQ when I get there. So O over X, or O times OX, that distance, divided by XP, and OY divided by YQ, if those are the same, that guarantees then that this side is going to be parallel to the third side that it does not cross. That's only if the proportion is true. If that proportion is not true, then we have to try something else. So let's go ahead and try these. We've got two examples. One's going to go the forward direction, one's going to go with the converse. But for number 1 here, I want to suppose that MN and ST are parallel and split the triangle into lengths shown below. These are all in inches. We need to figure out Rn. So first of all, I want to find Rn. I'm going to label it X here because it's going to be a little easier to talk about that. Well, what I would look at is X is a portion of the side RT, which is the bigger part of the triangle. So if I look here, that portion is going to be split and created by my segment NM. Well, I do know that MN and ST are parallel. So since I have my parallel side, it's creating my two split pieces here. I have my X and my 120. Those are going to be the split parts that are created by that segment. I also have the 140 and the 80, which are the other two split parts on the other side. I have the 3 of the 4 split parts, so I can set up my proportion. Now again, you can set this up any way you want. I will pretty much always just use that line as my fraction bar. So I'm going to set this up as X over 120 is going to equal 140 over 80. And then if we want to solve this, we solve this the same way that we solve all of our proportions, which is going to be to cross multiply. So I'm going to multiply x times 80. That gives me 80x. That is going to equal 120 times 140, which you can do real quick on a calculator, but it is 16,800. Then we go ahead and divide by the 80 on both sides. And we get an answer here for x of 210. And that again is in inches. So I do want to make sure that that makes sense. And if I put that 210 in this place, I know 120 is going to be smaller than the 210, and the 140 is definitely bigger than the 80. So that kind of matches up to where my bigger side is actually on top, the smaller part is towards the bottom. That does seem to fit what I have. Now let's look at part B. Part B, I'm looking to find ST. Now ST is the full third side. So the most important thing that I can point out here is that this is talking about a full side, where part A was talking about what I would call a split side. It's just some portion of that full side. And so I'm going to do this differently. With the full side, I have to compare full sides of two different triangles. So what I'm going to actually do here is I'm going to use the fact that I have two similar triangles here, and that those are going to have to be proportional. Okay, and I know I have similar triangles mostly because of this parallel piece here. My corresponding angles at T and N and at S and M are going to be equal. So there's your angle. You could also use angle R shared between the two, so that one's also the same. So definitely similar triangles, but I have to compare full parts of those triangles. So I'm going to call my missing side STY here. So to set this one up, I'm going to actually use this third side, this parallel piece, the 168, and I'm going to divide it by Y. That's the smaller triangle divided by the larger triangle. So what I need to do is find another side where I know everything. Well, I could use X here because I found that side. I could add it to RT and do some work with that. However, whenever you have the chance, you should always go back to the measurements you were given, just in case we made a mistake along our way in part A. So I'm going to go back to the 140 and the 80. So I can use the 140 because that's the smaller part of this top triangle. The problem is 80 is not part of the full triangle. So what I have to do here is just a quick little side math. I need to figure out what is this entire side from R to S. Well, that's the 140 plus the 80, which means this is going to be 220. So that's going to be the piece that I use along the bottom. Now I have my proportions set up. So again, I can do my cross multiplying. When I do that, I'm going to have 168 times 220 and 140 times y. So I'll start with 140 times y. That's 140y is equal to 168 times 220, which is 36960. Then we can go ahead and divide by our 140 on both sides. And I get an answer here for y of 264, and that is in inches. So that gives us kind of that third side, okay, and we now have that measurement. Okay, at this point we're going to go ahead and switch to our other theorem here, which was our Converse theorem, and using this I can actually prove that things are either parallel or not. To do that, what I have to do is set up my proportions of my missing sides to see if these actually are congruent. So to do this, I'm actually using the converse, which means I'm asking myself if these are proportional. So I'm going to create my proportions and I'm going to see if they're actually the same. So these are going to be my two fractions. Again, I just use the sides as they show up here. So I'm going to use the 12 and the 3. So I'll just do 12 over 3. And then 8 and 2. 8 divided by 2. The question is, are those actually equal? And so we need to check. We can actually divide these out. 12 divided by 3 is 4. And 8 divided by 2 is also 4. Since those are the same, it does check, which means that this is a proper proportion. It is proportional. So I can say that these are going to be parallel. So I'm going to say yes, xv is parallel to yz. And the reason I know that is by the side splitting converse theorem. Okay, and it's by the converse because I am going the other direction. Okay, I'm not starting with my triangle trying to find missing pieces using the proportion. I am using the proportion to show that I have those parallel parts. Alright, so that is going to go ahead and finish up our video here for 13.3. We will see you next time where we'll dive into some trigonometry.